of rotating equipment in a plant are driven by motors or other sources of power through shaft couplings. For the equipment to operate smoothly, the shafts that are coupled together have to be properly aligned. If the shafts are misaligned, bearings, seals, and couplings can wear excessively, leading to premature equipment failures. In order to prevent these problems, you need to know how to perform a shaft alignment. Before you can properly align two shafts, you need to determine the amount of misalignment. This arrangement of instruments and equipment can be used to measure parallel and angular misalignment. This is done by rotating the shafts and taking readings from the dial indicators at certain points in the rotation. Now let's see if you can answer a question about the information that we just covered. Before you start taking measurements for a shaft alignment, you need to make sure preparations are made. First of all, the equipment that you'll be working on must be isolated, tagged, and locked out according to your plant's procedures. This is done to keep someone from starting the equipment accidentally while you're working on it. You'll also need to identify and correct any conditions that could force the equipment out of alignment or cause inaccurate measurements during the alignment procedure. Some of these conditions include pipe strain and problems with the foundation that the equipment is mounted on. The space or gap between the coupling hubs should also be set before the alignment. If the gap is not correct, the coupling could be damaged by axial movement of the shafts when the equipment is put back in service. In addition, it's good practice to perform a rough alignment on the equipment. This helps to ensure that the amount of misalignment will not be beyond the range of the instruments that will be used when more precise measurements are taken. Most of the general things that you need to do to prepare for an alignment are the same, regardless of the type of alignment method that you plan to use. However, a few preparations may be done a bit differently for different alignment methods. For example, since the reverse dial method involves mounting brackets on the equipment shafts, the shafts are smoothed with a light abrasive to remove any burrs or bumps that could cause the brackets to rock or slip out of position. Once the brackets and dial indicators are set up on the pump and motor, the distance between the brackets is measured. This measurement will be used to set the brackets up for the bar sag measurement. This mechanic also marks the shafts so he'll know where to mount the brackets later. Then the brackets are mounted on a shaft or pipe so the distance between them is the same as it was on the pump and motor shafts. Since there are two bars involved in the reverse dial method, both dial indicators are zeroed. Next, he rotates the test fixture 180 degrees. Then he takes readings from the indicators. At this point, we've done the pre-alignment preparations and we've taken our tape measurements. The next step would be to take a set of readings with the dial indicators. For now, though, take some time to answer a question about the information that we covered. In this section of the program, we reviewed some principles of shaft alignments, and we saw how dial indicators are set up for a reverse dial alignment. We also reviewed the preparations for an alignment. Now try some practice questions. To do that, we're going to take dial indicator readings and record them on a data sheet. The procedure we'll follow begins with the S dial indicator at the 12 o'clock position and the M dial indicator at the 6 o'clock position. The face of each dial indicator is adjusted to read 0 and then tightened into place. Before readings are taken, the shafts are rotated a full 360 degrees and the dial indicators are rechecked for 0 readings. If either indicator doesn't read 0, it's possible that a bracket slipped or that the rotation wasn't exactly 360 degrees. Once the dial indicators are adjusted, the mechanic takes vertical plane readings by rotating the shafts 180 degrees until the S dial indicator is at 6 o'clock and the M dial indicator is at 12 o'clock. Then he takes readings from both dial indicators and records them on the data sheet. Now the mechanic takes another set of readings to make sure the first set is accurate. If the second set of readings isn't the same as the first, it means that something has shifted and he'd have to retighten the brackets and start over. But in this case, the readings are the same. The next step is to put the information from the data sheet into graphs, formulas, or an alignment computer to find out how much to move the motor to correct the misalignment. But let's stop here to give you a chance to check your understanding of what we've covered in this part. Let's assume that you're about to take vertical misalignment readings on a pump and motor using the method that was taught in the lesson. The process of aligning equipment in the vertical plane involves taking measurements and then using the measurements to determine how to correct misalignment. In this section of the program, We'll plot a graph to determine how to correct vertical misalignment. Then we'll see how to actually move the equipment into vertical alignment. In the example we just saw, thermal growth was not a factor in determining the amount of misalignment. Thermal growth is the movement that occurs as rotating equipment reaches its normal operating temperature. Using a graph is one way to determine how much to move a component to correct for misalignment in the vertical plane. Another method uses formulas instead of a graph. If you would like to see that method, select the button labeled Formulas. When you're ready to see how to move the motor into alignment, select Go. The mechanic has the shim sizes he needs. The size is usually stamped on the shim, but it's still a good idea to measure the thickness with a micrometer to double-check the accuracy. To install the shims, the bolts for the motor's feet are loosened. Then the motor is lifted with a pry bar to slide the shims under the motor feet. When you're adding shims, it's best to use as few shims as possible. A stack of several shims could shift or flex and cause misalignment. When the shim packs are in place, the mechanic retightens the bolts for the motor's feet. At this point, the misalignment in the vertical plane has been corrected. However, it's a normal practice to take another set of readings and make sure the alignment is within tolerances. It's important to remember that if you need to factor in thermal growth during the procedure, the pump and motor shafts will be misaligned at ambient temperature. When the two components reach their normal operating temperatures, their shafts will be aligned. Now it's a good time to check your understanding of how to graph and correct vertical plane misalignment. In this part of the program, we're going to measure horizontal misalignment between a pump and a motor. We'll take dial indicator readings and record them on a data sheet. To measure horizontal misalignment, the mechanic will zero the S dial indicator at the 3 o'clock position and the M dial indicator at the 9 o'clock position. Next, he rotates the shafts 360 degrees to make sure the indicators still read 0. They do, so he's ready to take his readings. He rotates the shafts 180 degrees, so the S indicator is at 9 o'clock and the M indicator is at 3 o'clock. The mechanic is taking a second set of readings to confirm that his first set was accurate. Once he confirms his readings and calculations, the values from the data sheet can be put into a graph, formulas, or an alignment computer to determine how to correct the horizontal misalignment. For now, let's see if you can answer a question on the information that we covered in this part. To correct horizontal plane misalignment using the reverse dial method, measurements are taken and recorded on a data sheet. Then information from the data sheet can be used in a graph to show how to align equipment. Another way to determine how much to move a component to correct for misalignment in the horizontal plane is with formulas. If you'd like to see that method, select the button labeled Formulas. When you're ready to see how to move the motor into alignment, select Go. To move the motor into alignment, the mechanic will use continuous type dial indicators on both an inboard foot and an outboard foot. Continuous type dial indicators give only positive readings. The indicators are mounted so their stems are pushed in and then set for the amount of movement required. In this case, the outboard dial indicator is set to 18 mils and the inboard indicator is set to 14 mils. Then he loosens the bolts for the motor's feet. The mechanic shifts the motor into alignment by turning a set of jacking bolts and watching the dial indicators. When both indicators read 0, the move is complete, and the motor should be aligned with the pump in the horizontal plane. Now the mechanic retightens the bolts at the motor feet. As he tightens each bolt, he checks the dial indicators to make sure the motor doesn't shift. After all the bolts for the motor's feet have been tightened, the shafts of both components should be aligned in the horizontal plane. However, it's a good idea to take another set of alignment readings and make sure the alignment is within tolerances. Let's see if you understand how to graph and correct for horizontal misalignment. In this section of the program, we looked at how to perform reverse dial alignments. Now try some practice questions. One of the fastest and easiest methods of performing a shaft alignment is with a laser alignment system. We'll use this particular system to explain how a laser-based alignment is done. This is the laser. It's installed on the pump's shaft. During operation, the laser emits a low-intensity beam. The beam is detected by a device called a receiver or detector, which is mounted on the motor's shaft. As the shafts are rotated during an alignment, the beam will hit the circular face of the receiver at different points. The location of the beam on the receiver is related to the misalignment between the two shafts. The receiver is connected to a computer. The computer uses the information it receives from the receiver to calculate how much misalignment exists and how to correct the misalignment. Like other types of alignment equipment, laser systems are precision instruments, so you have to be careful when you set them up and operate them. In addition, laser systems may not perform accurately under certain conditions. Heavy concentrations of dust or vapor, such as steam, can block or distort the laser beam. Also, strong sunlight can affect the system's performance, so you may need to shield the laser beam when readings are taken under certain conditions. Another precaution that needs to be taken with laser systems involves personal safety. Lasers can damage your eyes, so never look directly into the beam. Normally, the manufacturer's manual will list safety precautions and conditions that can affect the particular system that you're working with. Many of the preparations for a laser-based alignment are the same as those made for other alignment methods. You should inspect the equipment and fix any condition that could cause shaft misalignment. You also need to perform a rough alignment before setting up the laser equipment. A typical equipment orientation for an alignment is to have the stationary component on the left and the movable component on the right. To assemble the system, the mechanic first installs the brackets for the laser and the receiver. When the brackets are locked on, the instruments slide onto them. Next, he turns on the computer. Now that the equipment is set up, the alignment procedure begins with tape measurements. With this system, the first measurement is the diameter of the coupling. In this case, the coupling diameter is 3 inches. The mechanic enters that measurement into the computer. After he does, the computer display prompts him for the second measurement. The second measurement is the distance from the center of the coupling to the receiver. That distance is also 3 inches. He enters that measurement into the computer, and then the computer tells him what to measure next. The next measurement is between the receiver and the center line of the bolt for one of the motor's inboard feet. This measurement should be taken parallel to the motor's shaft, so he uses the bracket chain, which is directly under the receiver, as a reference point. Then he enters the measurement, which in this case is 6.5 inches. So he measures the distance between the center lines of the bolts for the feet and enters the measurement, which is 12 inches. Now the laser has to be lined up so it shoots the beam into the center of the receiver. First, he turns on the laser and centers the beam on the receiver's dust cap. He leaves the cap on to see the beam better. Once the beam looks centered, he removes the cap to allow the receiver to see the beam. Next, he calls up a special display on the computer so he can center the laser beam on the receiver more precisely. The dot represents the location of the beam on the receiver. The beam can be moved using thumb wheels on the laser assembly. It can be moved side to side and up or down until it's centered. The computer display indicates when the beam is centered on the receiver. At this point, the computer has the tape measurements it needs, and the laser beam has been adjusted. The next step is to take alignment readings. With most alignment methods, the pump and motor shafts are rotated, and readings are taken at specific points called clock positions. It's important to know where the clock positions are, so the readings can be taken at the correct spots. However, this particular system has built-in sensors that detect the angle of rotation. Once the mechanic starts the procedure, the system continuously takes readings and compares the readings to the positions of the laser and the receiver as he rotates the shafts. This system needs a minimum of a quarter turn to gather the data it needs. After rotating the shafts, the mechanic pushes a button to stop taking readings, then presses another button to display the amount of misalignment. To align the motor using this laser system, the mechanic activates a function that keeps track of the motor's movements as they're made. First, he adjusts the amount of shims under the motor's feet. This corrects the vertical misalignment. To correct the horizontal misalignment, the mechanic shifts the motor using jacking bolts and monitors the indications on the computer. The graphic of the motor's shaft moves toward the desired center line as the motor is moved closer to the correct horizontal position. After he's made the required moves, the mechanic tightens the motor bolts. The computer display will tell him if the motor shifts out of position as the bolts are tightened. At this point in the job, a second set of readings would be taken to recheck the alignment. The alignment should be within the tolerances specified for the equipment. Now try a question on the information that we covered. In this section of the program, we looked at one type of laser alignment system and how it's used. In addition to measuring misalignment, some laser systems can also be used to detect or measure other conditions, such as soft foot, that can affect the operation of equipment. However, the laser system can only produce accurate results if it's used properly. With that in mind, try some practice questions now. How do laser alignment systems typically determine shaft misalignment as the equipment shafts are rotated?